Now we move on to the second part, which is the variational principle. This is the most important theory introduced in the recent paper of Das, Fisherman, Simons, and Urbanski. So we need a couple of notions to get to the statement of the variational principle. So first, we're going to talk about the successive minima functions. So because many definitions, this section will be complicated. So I hope I will have time to provide a concrete example. Instead of using the Beamer, I'm gonna switch to the tablet writing at the end to help illustrate this whole idea. So let's take D to be m plus n. Remember, mn corresponds to the m by n matrices. And there's notion called the jth minimum of a lattice with respect to some fixed norm in Rd. So this is defined to be the minimum of the lambda, such that the set of R in the lattice lambda is bounded by little lambda that contains j's linearly independent vectors. So for m by n matrix A, the successive minima function of the matrix A denoted as a vector valued function from positive numbers to Rd is defined by the following formula. This hi is ith component of this vector valued function. It is defined to be a logarithm of the lambda I, which is the ith minimum of the lattice, lambda I of GTUA of ZD. So now we can translate the Daniel's correspondence principle in the language of the successive minima functions as shown in this table. The definitive properties of A corresponds to the dynamic properties, now the orbits. A being badly approximable, corresponding to the limb soup of the negative part, the negation of the first component of the successful minima function is bounded as t goes to infinity. And t being singular means the limb inf of this guy is infinity. And A being very well approximable, corresponding to the limb soup, this first component of the negation of the first component of the successful minima function can blow up at least linearly. Okay. So next notion is called the templates. Elementary but highly technical. An m by n template is a piecewise linear function, piecewise linear map with D components with the following properties. First, there's a monotonicity in terms of the components of this template. And secondly, the derivative is bounded below and bounded from below and from above. Below by 1 over n, negative 1 over n, and above by 1 over n. And the third one is more complicated. The possible slopes of the sum of those components, the first j's components of a template, it cannot be arbitrary. It can only be those rational numbers. as long as they are on the interval where fj is less than fj plus 1 on that interval. There's a fundamental relation between the templates and the successive minimum functions given by the following theorem in DFSO's paper. So first, for every m by n matrix A, so we automatically have a successive minimum function with respect to A. And the theorem says there always exists a template such that their difference is bounded by a constant number. So this means the difference between those, this notation means the difference between those two notations is bounded by a constant number. The constant number might depend on D, which in turn depends on M and N, but nothing else. And conversely, for every M by N template F, we can find a matrix, M by N matrix, such that the successive minima function is the difference between the successive minima function and F is also bounded by a constant that depends only on M and N. The significance of this theorem, so the study of the matrix can be translated into the study of the properties of the successive minimum functions through the Daniel's correspondence principle, and in turn, through this theorem, it can be translated into the study of the templates. So the next notion is quite complicated. So instead of using the slides, I think it would be better for me to switch to the tablet writing. So now we move on to the statement of the variational principle. Before we state that, we still need one more definition. A collection of templates is said to be closed under finite perturbations if whenever we have the difference of two templates that's bounded by a constant, we have a G that's contained in this collection of templates. The reason that we introduce this definition is that sometimes studying a single template is harder than study the collection of some properly chosen templates. So this is the first version of the variational principle given in this paper. Let F will be a collection of templates. Now, you remember that the templates are always piecewise linear. Each component of a template is always piecewise linear. So those maps are always programmable. Closed under finite perturbations. So given as the definition here, then the dimension of the set of the matrices associated to the templates. Sorry, this my mistake. I should say this first. So D of S, for S being a collection of Borel functions, is the set of matrices where the successive minimum function is in this collection. The Hausdorff dimension of set is given by the supremum of lower contraction rates of the templates in F. And likewise, the packing dimension of the set of matrices here is given by the supremum of the upper contraction rates of the templates in F, as we just introduced. The second version of the variational principle says if you have a collection of derived functions, which is closed under finite perturbations, which are not necessarily consist of the templates, then if we take the we can restrict our supremum to those templates in S. Previously, this was my typo. There should be P here, the packing dimension. Okay. The version 3 is about the relation between the Hausdorff and packet dimension and the lower and upper contraction rates. If you have a lower bound for the Hausdorff dimension or packing dimension, then there exists a matrix and a template, and which is close enough to the successive minima function with respect to A, then the corresponding lower or upper average contraction rate also has this lower bound, and vice versa. The second part is the converse of the first one. Okay, now let's talk about the dimension games. This is a key strategy in the proof of the variational principle. The dimension games was introduced by Wolfgang Schmidt in 1950s. So here, I'm going to give you a very basic version of this. Given the parameter beta between 0 and 1, so Alice and Bob will play the so-called delta dimensional Hausdorff or packing beta game as follows. Alice begins by choosing a starting parameter radius as denoted by rho naught. So during the kth turn, so Alice chooses a non-empty finite 3-row k separated set. So this means every 2 points in AK has distance at least 3 rows of k. And Bob responds by choosing a closed ball that's centered at x sub k with radius rho sub k. And this x sub k is an element in this 3-row k separated set. At the beginning, there's no any restrictions on the Alice choice, but on each subsequent turn, k plus 1, Alice will choose a sub k plus 1, so that this a sub k plus 1 is contained in this ball, centered at x sub k with radius 1 minus beta times rho sub k. And after infinite many turns have passed, because those b sub k's are closed balls, I take the infinite intersection because they have the descending radius converted to 0. You can find a point in the limit. So this will be called the outcome of the game. We consider the sequence of sets, and we compute the following two numbers. So this lower delta is the lim-inf of this sum of a logarithm of the number of elements in AI divided by the negative log beta. And this upper delta is the lim-sup of that. Now we say a set is a set S in Rd is said to be delta dimensionally Hausdorff or respective packing, meaning if Alice has a strategy to simultaneously ensure that this x sub infinity is in set S, and that will score this lower delta and upper delta, or respective upper delta is at least delta. So we have two we have parameter delta and the set to begin with. And the criterion for winning is that this x infinity is s, and this score as computed here is at least delta. Remember that we have a parameter beta here. We start with a beta between 0 and 1. The set S is said to be a delta dimensional Hausdorff winning or respective packing winning if it is beta winning for all sufficiently small beta greater than 0. So to relate this notion to the Hausdorff or packing dimension of a Borel set, here's a theorem due to Das, Fisherman, Simons, and Urbanski. So the Hausdorff or respective packing dimension of a Borel set is the supreme of this delta, such that this S is delta dimensionally Hausdorff or respectively packing winning. This is how we associate this topological game, and the dimension theory.